When the 20th century was just beginning, scientists believed they understood the basic rules of nature. Electricity, magnetism, and classical mechanics had formed a powerful framework that explained the motion of planets, the path of a bullet, and even the behavior of heat and light. Yet one mystery remained untouched at the heart of all matter: the atom itself. It was impossible to see, impossible to touch, but its behavior shaped everything in existence. Classical physics tried to describe this hidden world, but the deeper researchers looked, the more the laws they trusted began to fall apart, and into this confusion stepped a young Danish physicist named Niels Bohr, armed not with a new instrument, but with an idea bold enough to challenge centuries of scientific certainty. Atoms, according to classical physics, should have been unstable. Electrons circling the nucleus, charged particles in motion, were expected to lose energy continuously. They should spiral inward like planets falling into their star, collapsing the atom in less than a millionth of a second. But this was not happening. Matter was stable. The world existed. Something was wrong with the old assumptions. The atom refused to behave like a miniature solar system, and no experiment could force it to reveal its secrets through classical reasoning. The failure to explain atomic stability had become a crisis, threatening to undermine the very foundation of physics. Then came the revolutionary proposal from Bohr. He suggested something that sounded almost impossible: electrons do not move in continuous orbits like planets. Instead, they exist in very specific, fixed energy levels. They cannot exist between these levels, and they cannot gradually slide from one to another. Their behavior is not smooth but quantized, divided into distinct steps rather than flowing curves. This single idea, electrons locked in defined energy layers, became the spark that illuminated the entire atomic world. To understand the courage behind Bohr's proposal, imagine the scientific atmosphere of the time. The idea of quantization had only recently emerged through Max Planck's work on blackbody radiation, and Einstein had extended it to explain the photoelectric effect. But applying quantization to the atom was far more daring. It meant rewriting the architecture of matter itself. Bohr believed that the electron's motion inside the atom was governed not by classical continuity, but by quantum restrictions that dictated where electrons were allowed to be. If electrons were confined to certain orbits where they did not radiate energy, the atom would achieve stability. The collapse predicted by classical physics would never occur because electrons would not behave like tiny mechanical planets. They would follow entirely new rules. This proposal seemed absurd to many scientists. How could an electron simply choose not to radiate energy? How could it suddenly leap from one orbit to another without occupying the space in between? Yet Bohr insisted that nature did not owe classical physics an explanation. Instead, classical physics owed nature its obedience. At the atomic level, old rules did not apply. Bohr embraced this mystery rather than rejecting it, and that boldness became the foundation of his model. One of the remarkable qualities of Bohr's idea was its simplicity. The atom could be stable if electrons were allowed to occupy only certain energy levels, each defined by an integer number. These orbits acted like the rungs of a ladder. You could stand on one rung or another, but nowhere in between. Electrons could move between these levels only by absorbing or emitting a very specific packet of energy. This was the dawn of the concept known as the quantum jump. It was a behavior completely foreign to classical thinking, yet it elegantly explained how atoms absorbed or released light without breaking apart. Bohr's fixed energy levels also explained something that had baffled scientists for years: the spectral lines of hydrogen. When hydrogen gas is heated or electrified, it emits a series of bright lines of specific colors. No one could explain why these lines occurred at such precise frequencies. Bohr's model changed that in a single stroke. Each line corresponded to an electron jumping between two specific energy levels. The difference between the energy levels determined the color of the light. With breathtaking accuracy, Bohr's equations predicted the exact positions of these spectral lines. For the first time, The atom was not just imagined. It was mathematically described, detailed, predictable. A structure once hidden in total darkness suddenly became visible through the lens of quantum theory. But the success of Bohr's model was not only in solving old puzzles, it was in reframing how scientists thought about nature. The idea of fixed energy levels forced physicists to confront a new reality. The microscopic world obeyed different rules. Deterministic paths gave way to quantized states. Certainty faded into probability. The universe, at its smallest scale, was not a smooth, continuous fabric but a mosaic of discrete pieces. Bohr's model was the bridge between the classical world everyone understood and the quantum world no one had yet imagined. The idea of electrons in fixed energy levels also introduced a new concept of atomic architecture. Instead of chaotic motion, there was order. Instead of collapse, there was balance. These energy layers determined the chemical behavior of atoms, the formation of molecules, the bonding between elements, and the structure of the periodic table. The modern world, from chemistry to biology to material science, rests on this understanding of atomic stability. Without the idea of fixed energy levels, everything from the behavior of metals to the existence of stars would remain a mystery. Bohr's insight also revealed something profound about the limits of human intuition. The atom did not resemble anything from everyday experience. Its behavior was alien, unpredictable, almost paradoxical. And yet Bohr recognized that nature did not exist to be comfortable or familiar. The task of science was not to force reality into human expectations, but to reshape human expectations to match reality. His model forced scientists to abandon old prejudices and embrace the strange and elegant rules of the quantum universe. Even though later developments in quantum mechanics replaced some features of Bohr's model, the core idea, fixed energy levels, remained untouched. Modern quantum theory describes electrons not as particles in rigid orbits, but as clouds of probability, yet the allowed energies remain quantized exactly as Bohr proposed. His insight survives at the heart of atomic theory, echoed in the equations of Schrödinger, the uncertainty of Heisenberg, and the principles of quantum field theory. Every modern interpretation of the atom carries the imprint of Bohr's revolutionary idea. Bohr's contribution was not just a scientific theory, it was an intellectual revolution. It proved that the universe was deeper, more mysterious, and more structured than classical physics could ever describe. It opened the door to the quantum age, an era that gave birth to nuclear physics, semiconductors, lasers, GPS technology, medical imaging, and the foundations of modern computing. The idea of fixed energy levels, an idea once considered impossible, became the first blueprint for understanding the microscopic world. This is why Bohr's name remains etched in the history of science. He dared to imagine the atom not as classical mechanics demanded, but as nature required. He gave order to the previously chaotic idea of electron motion. He explained stability, structure, and light itself through the quantization of energy. And he did this with a clarity that allowed others to build the towering framework of quantum mechanics on the foundation he laid. The story of Bohr's model is the story of a scientist willing to step beyond the known, into the shadows of the unseen, and bring back a new vision of reality, one that transformed our understanding of the universe at its deepest level. As Bohr's ideas began to circulate in the scientific world, a quiet shock spread through the physics community. Many admired his courage, while others resisted the strange new picture of the atom he presented. Yet even the critics could not ignore one undeniable fact. Bohr's model worked. It predicted the hydrogen spectrum with uncanny accuracy, something no theory before had been able to accomplish. Scientists who once doubted him found themselves confronted not by speculation, but by results. And in physics, results have the final word. But the true significance of Bohr's fixed energy levels stretched far beyond a single element or a single spectral series. What he introduced was a new framework for understanding all matter. It was as if he had revealed a hidden architecture built into every atom in the universe. Before Bohr, the atom was a puzzle of conflicting ideas. After Bohr, it became a structured system governed by the laws of quantized energy. The science of the microscopic world had finally found its foundation. Yet the revolutionary power of Bohr's insight came not just from what it explained, but from what it demanded. No longer could physicists assume that the laws of classical mechanics applied at every scale. The rules that governed planets and pendulums did not describe electrons. The tiny world obeyed its own logic, one that cared nothing for human intuition. Bohr forced science to confront this divide. It was a painful realization for many. Classical physics had been their trusted guide, the system that explained everything from falling apples to orbiting moons. But now it stood powerless before the structure of the atom. The quantum world was waiting, and Bohr had opened the door. The fixed energy levels became a kind of cosmic scaffolding on which the entire structure of modern physics would be built. They explained why atoms emit light in specific colors, why elements combine in predictable ways, and why matter possesses stability across time. But the implications stretched further. These energy levels dictated the chemical identity of every substance. The number of electrons in each level determined whether an element behaved like a metal, a gas, or something in between. They shaped the interactions between atoms, the formation of molecules, and the forces that allowed life to exist. From the behavior of water to the structure of DNA, the echoes of Bohr's quantized orbits ripple through every corner of the natural world. The documentary story of Bohr's insight also carries a deeper message about the scientific journey. Progress is rarely smooth. It comes through tension, conflict, and the willingness to abandon familiar ideas. Bohr himself faced countless questions. Critics asked how electrons could leap from one orbit to another without traversing the space in between. They questioned how an atom could choose a particular energy level. These were not trivial concerns. They struck at the heart of classical thinking, which insisted that all motion must be continuous. Bohr accepted these mysteries, not because he had all the answers, but because nature was pointing in that direction. Experiments confirmed quantized behavior, and his model gave those observations a coherent structure. With time, Bohr's fixed energy levels began to inspire a new generation of physicists. Young minds like Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger took the torch forward. They developed matrix mechanics, wave mechanics, exclusion principles, and new mathematical tools that transformed Bohr's conceptual model into the fully developed framework of quantum mechanics. Yet even as these advances expanded the theory, they preserved Bohr's essential insight: electrons can occupy only specific energy states. This idea remained untouched, a constant truth at the heart of the new theory. The world of the atom still lived on quantized steps, not continuous slopes. Another remarkable consequence of Bohr's fixed energy levels was their role in shaping the technologies of the future. When electrons jump between energy levels, they release or absorb specific packets of energy. This simple fact is the backbone of modern electronics. The lasers that cut metal, the LEDs that light screens, the semiconductors that power computers, and the atomic clocks that keep time for GPS satellites all rely on the behavior of electrons in quantized states. What began as a theoretical insight into the hydrogen atom became the technological foundation of the 21st century. Bohr could not have predicted the digital world we live in, yet his fingerprints are on every device, every circuit, every photon emission that carries information across the globe. As scientists explored deeper into the atomic world, they discovered more complexities, more layers of structure that refined Bohr's simple model. But rather than replacing his work, these discoveries strengthened it. Bohr's model was not the final answer, it was the first correct answer. It pointed in the right direction, showing that electrons were not free to roam continuously, but were restricted by quantum rules. Later models replaced orbits with orbitals, turning Bohr's circular paths into regions of probability. Yet the underlying principle remained unchanged. Matter behaves according to quantized energy, and those quantized energies determine the structure of atoms. In every quantum equation, in every energy diagram, the legacy of Bohr's insight is unmistakable. The story of Bohr's fixed energy levels also reveals the emotional landscape of scientific discovery. Breakthroughs are not just intellectual events, they are human events. Bohr himself struggled with self-doubt. He wrestled with the implications of his work and the resistance of the scientific community. But he continued because he believed the universe would reward the pursuit of truth. When his model succeeded, it changed not only the direction of physics, but the trajectory of his own life. He became one of the most influential scientists of the 20th century, a mentor to many of the great minds who followed, and a guiding voice in the debates that shaped quantum mechanics. As his ideas gained acceptance, they began to influence the philosophy of science itself. Bohr introduced the concept of complementarity, the idea that two seemingly contradictory descriptions can both be true depending on the context. This idea grew naturally from the behavior of electrons in fixed energy levels. How could something behave like a particle in one scenario and like a wave in another? How could it jump between states without moving through space? Reality at the quantum level rejected all simplistic interpretations, and Bohr embraced that rejection. The fixed energy levels were not just a physical description, they were a philosophical challenge to the human desire for certainty. The influence of Bohr's model reached beyond the laboratory and touched the very way humans perceive the universe. It taught us that the world is not always intuitive, not always predictable, and not always comfortable. It taught us that truth can exist outside the limits of human experience. The atom, once thought to be a solid, indivisible building block, revealed itself to be a symphony of probabilities governed by invisible laws. And Bohr was the first to give that symphony structure. As we reflect on the significance of Bohr's fixed energy levels, we see how a single idea can reshape an entire field. It was not just a correction to classical physics, it was a transformation. It guided the development of quantum mechanics, inspired new theories, and pointed the way to technologies that define the modern world. It provided clarity where confusion once reigned and offered a new blueprint for understanding the fundamental behavior of matter. Bohr's model stands as a testament to the power of human curiosity and the courage to challenge what seems obvious. Even today, more than a century later, every student of physics encounters Bohr's energy levels. Every researcher who studies atoms, molecules, or quantum systems builds upon the foundation he laid. His insight has survived revolutions, refinements, and reinterpretations. The atom remains quantized, electrons remain confined to specific states, and the universe, as Bohr revealed, continues to operate according to rules that are as mysterious as they are beautiful. His work reminds us that scientific progress does not happen by clinging to the familiar, but by stepping into the unknown. Bohr did not simply propose a new model, he reimagined the nature of reality. His fixed energy levels continue to echo through every experiment, every theory, and every breakthrough in modern physics. They are a permanent part of the story of science, a moment when a young physicist dared to describe the invisible world in a way no one had imagined, and got it right. This is the legacy of Bohr's revolutionary idea. It transformed physics, reshaped technology, and forever changed our understanding of the universe. It stands as one of the greatest intellectual triumphs in human history, proving that even the smallest parts of nature can reveal the largest truths about existence. In the early years of the 20th century, the atom was still a mystery, a tiny world hidden from view, governed by laws that defied common understanding. Scientists could glimpse fragments of its behavior, but the deeper they looked, the more paradoxical it became. Electrons seemed to orbit the nucleus like planets, yet classical physics predicted their inevitable collapse. Radiation should cause atoms to fall apart, and yet matter persisted. It was in this climate of uncertainty and incomplete knowledge that Niels Bohr introduced a concept that would change the way humanity understood the atomic realm: quantum jumps. These were no ordinary ideas. They were radical, even unsettling. They suggested that electrons did not move smoothly through space as classical mechanics demanded. Instead, they leapt abruptly between fixed energy levels, appearing in one state, and then instantaneously in another, without traversing the space in between. To grasp the significance of this idea, it is important to imagine the mental landscape of the physicists of the time. The atom was often visualized as a miniature solar system, with electrons moving in circular or elliptical paths around a central nucleus. This model, while intuitive, could not account for stability or spectral emissions. Scientists were stuck between a familiar analogy and the stubborn reality of the quantum world. Bohr's concept of quantum jumps disrupted this familiar vision. He proposed that electrons could only exist in discrete energy states, and that transitions between these states were instantaneous. These transitions were not continuous movements, but sudden, defined leaps. The world of the atom was not a flowing, smooth continuum, it was a series of steps, invisible yet profoundly structured. At first, the idea of electrons leaping through empty space seemed almost magical. How could a particle disappear from one location and reappear in another without occupying the intermediate space? Classical intuition screamed that such behavior was impossible. Yet experimental evidence supported Bohr's notion. The precise spectral lines of hydrogen, which had confounded scientists for decades, could be explained only if electrons moved abruptly between energy levels. Each jump released or absorbed a discrete amount of energy, corresponding exactly to the color of light emitted or absorbed. This was the birth of the concept of quantized energy transitions, a cornerstone of modern quantum physics. Bohr's daring proposal transformed a confusing pattern of observations into an elegant and predictable system. The idea of quantum jumps carried implications far beyond the behavior of a single element. It challenged the very notion of continuity in nature, a principle that had been assumed unquestioningly since Newton. In the macroscopic world, motion appeared smooth and predictable, but at the atomic scale, Bohr revealed a different reality. Nature, it seemed, operated in leaps and bounds, not in gradual, observable transitions. This insight reshaped the scientific understanding of the atom and provided the foundation for the emerging field of quantum mechanics. It was a radical departure from centuries of classical thinking, yet it matched reality with astonishing precision. Quantum jumps also introduced a new way to think about energy itself. Energy was no longer a continuous flow but existed in discrete packets, quanta, that could be transferred only in specific amounts. When an electron jumped from a higher energy level to a lower one, it released a fixed amount of energy in the form of light. Conversely, when it absorbed a photon of exactly the right energy, it could leap to a higher orbit. This concept not only explained the hydrogen spectral lines, but also provided a universal principle governing all atoms. The behavior of electrons was quantized, and the energy changes associated with their jumps became a predictable, measurable phenomenon. This understanding transformed the atom from a mysterious, invisible entity into a structured system with rules that could be studied, calculated, and applied. The concept of quantum jumps reshaped the way physicists approached the problems of atomic and molecular structure. Before Bohr, scientists struggled to reconcile the stability of matter with the predictions of classical mechanics. Electrons should radiate energy continuously and spiral into the nucleus, yet atoms remained intact. Quantum jumps resolved this paradox elegantly. By confining electrons to specific energy states and allowing transitions only in discrete leaps, Bohr provided a mechanism for stability. Atoms could exist indefinitely without collapsing, while still emitting or absorbing energy in precise, measurable quantities. This simple yet revolutionary idea bridged the gap between theory and observation, giving scientists a reliable framework to explore atomic behavior. Bohr's notion of electrons leaping between energy levels also had profound implications for chemical reactions and bonding. The energy differences between levels dictated how atoms could interact, form molecules, and share or transfer electrons. Quantum jumps explained the selective absorption and emission of light, the behavior of ions, and the reactivity of elements. Every chemical reaction, every spectral line, every quantum event in the microscopic world could be traced back to the behavior of electrons jumping between energy states. This realization not only advanced physics, but also laid the groundwork for the modern understanding of chemistry. The invisible dance of electrons, governed by discrete jumps, became the key to decoding the structure of matter. Bohr's idea also challenged the philosophical assumptions of science. Classical physics had always assumed determinism, that the future state of a system could be predicted with certainty if its present conditions were known. Quantum jumps shattered this notion at the atomic level. The exact timing of an electron's transition could not be predicted. Only the probability of a jump occurring could be calculated. This introduced a new element of uncertainty into physics, a recognition that the microscopic world was inherently probabilistic. Yet even within this uncertainty, order existed. The energy levels provided structure, and the quantum jumps maintained a balance that allowed matter to exist in stable, predictable forms. The universe was no longer a perfectly predictable machine, it was a probabilistic system, intricate, structured, and fascinatingly mysterious. The response of the scientific community to Bohr's idea was a mixture of awe, skepticism, and fascination. Many were reluctant to abandon classical intuition, and some derided the concept of instantaneous jumps as unscientific. How could a particle defy the continuous motion observed in the macroscopic world? Yet the evidence was undeniable. The spectral patterns of hydrogen matched Bohr's predictions with unprecedented accuracy. Experiments confirmed the quantized nature of energy exchanges, and slowly, the idea of quantum jumps gained acceptance. It became clear that reality at the atomic scale did not adhere to the smooth, continuous expectations of classical mechanics. Electrons did not move in familiar paths. They leapt between defined states, revealing a hidden order in the subatomic world. The discovery of quantum jumps also inspired further theoretical developments. Werner Heisenberg, inspired by Bohr, formulated the principles of matrix mechanics, describing the probabilities of transitions rather than exact trajectories. Erwin Schrödinger later developed wave mechanics, showing that electrons could be described as wave functions, yet their energies remained quantized, and transitions between states corresponded to Bohr's original leaps. Even in the refined mathematics of quantum mechanics, the essential concept of quantum jumps persisted. The electron may no longer be imagined as a tiny planet in orbit, but its energy states and transitions between them remained discrete and predictable, just as Bohr had proposed. His insight laid the foundation for a new era of physics, one in which the strange behavior of the atomic world could be understood, calculated, and harnessed. Quantum jumps also shaped the development of modern technology. Lasers, for example, operate directly on the principle of electrons moving between discrete energy levels, releasing photons in the process. The behavior of semiconductors, transistors, and LEDs all depends on the controlled transitions of electrons between energy states. Without Bohr's insight into quantum jumps, these technologies would not exist. The abstract concept of an electron suddenly leaping from one energy level to another became the practical foundation for devices that define the modern world, from communication systems to medical imaging to digital computing. Bohr's idea, once purely theoretical, found expression in every corner of contemporary life. In the context of scientific history, quantum jumps represented a paradigm shift. They forced physicists to abandon assumptions about continuity, determinism, and predictability at the atomic level. They introduced the concept of quantization as a fundamental principle of nature. They revealed a universe where stability, order, and structure emerged not from smooth motion, but from discrete transitions between allowed states. This insight transformed atomic physics from a speculative field into a precise, calculable science. It allowed generations of scientists to explore, experiment, and develop theories that would eventually lead to the full formulation of quantum mechanics, the most successful scientific framework in human history. Bohr's vision of quantum jumps also carried profound philosophical implications. It challenged the notion that nature could always be understood through classical logic or direct observation. The electron's leap was invisible, instantaneous, and counterintuitive, yet it was real and measurable through its effects. It taught scientists that the universe is not always accessible to intuition. Its deepest truths may be hidden, requiring both imagination and rigorous experimentation to uncover. Quantum jumps became a symbol of the strangeness of nature and the brilliance of human ingenuity in uncovering it. Even today, the concept of quantum jumps continues to resonate in physics. Experiments with single ions and atoms now allow researchers to observe these jumps in real time, confirming the principles Bohr introduced over a century ago. The idea remains fundamental to quantum optics, atomic clocks, and the study of quantum information. Bohr's insight, once theoretical, now underpins practical research at the cutting edge of science. His vision of electrons leaping between discrete states continues to guide our exploration of the microscopic world and our understanding of the universe's fundamental structure. Bohr's contribution through the idea of quantum jumps is a testament to the power of bold thinking. It demonstrates that progress in science often requires abandoning familiar concepts and embracing radical new perspectives. By proposing that electrons could transition instantaneously between energy levels, Bohr redefined the rules of atomic physics and provided a framework that remains essential to our understanding of matter. His idea challenged assumptions, solved long-standing mysteries, and laid the groundwork for the development of modern quantum theory. This transformative concept reshaped the study of the atom, turning an abstract puzzle into a system governed by discrete, predictable principles. It bridged the gap between observation and theory, linking the emission and absorption of light to the structured behavior of electrons. Bohr's insight illuminated the hidden architecture of the atom, revealing a universe more intricate and beautiful than previously imagined. Quantum jumps were not merely a theoretical curiosity, they were the key to understanding stability, energy transfer, and the fundamental behavior of matter. As the decades passed, the concept of quantum jumps grew in both depth and significance. Initially, it had been a theoretical solution, a bold mental construct devised to explain why atoms emitted light in discrete patterns and why electrons did not spiral into their nuclei. Yet as experimental techniques advanced, Bohr's idea transformed from an abstract hypothesis into a tangible observation. The development of spectroscopy, in particular, allowed scientists to measure atomic emissions with unprecedented precision. The spectral lines, once mysterious streaks of color, became the fingerprints of electron behavior. Each jump, each leap from one energy level to another, could be inferred with absolute clarity. The atom, once a shadowy enigma, revealed itself as a dynamic structure governed by invisible, yet exact, rules. Researchers began to see that quantum jumps were more than isolated phenomena. They were universal properties of matter. Electrons in all atoms, not just hydrogen, obeyed the same principle of discrete transitions. Whether in the simplest element or in complex molecules, energy changes occurred in quanta, not as a smooth flow. This universality underscored the power of Bohr's insight. His theory had not merely solved a single problem, it had uncovered a fundamental law of nature. Every electron, everywhere, moved according to these discrete rules. This was a profound shift in perspective. The atom was no longer a vague miniature solar system, it was a machine with steps, a world of precise jumps that could be understood, calculated, and ultimately manipulated. The realization that electrons could leap instantaneously between energy levels challenged classical notions of cause and effect. In everyday experience, motion is continuous and actions produce predictable reactions. But at the quantum level, Bohr revealed that transitions occurred without intermediate states. An electron did not slowly climb a ladder, it appeared to vanish from one rung and appear on another. The discontinuity of these jumps implied that nature, at its core, operated under different rules than those governing macroscopic objects. Classical mechanics, while extraordinarily successful in describing planets and projectiles, could no longer claim universal authority. The very idea of instantaneous change forced physicists to rethink the relationship between observation, measurement, and physical reality. The implications of quantum jumps extended far beyond atomic theory. They laid the groundwork for the emerging field of quantum mechanics, influencing every major advance in 20th century physics. Heisenberg's uncertainty principle, for example, was closely connected to the behavior of electrons during transitions. If electrons could move in discrete jumps rather than continuous paths, it became clear that certain properties, like position and momentum, could not be simultaneously known with absolute precision. Schrödinger's wave mechanics further developed these concepts, providing mathematical tools to describe the probabilities of jumps rather than fixed trajectories. Yet even in these more sophisticated frameworks, the essence of Bohr's insight remained unchanged. Electrons exist in discrete states, and transitions between these states define the behavior of matter. Quantum jumps also transformed the understanding of light and energy. Previously, scientists had struggled to reconcile the wave nature of light with its particle-like interactions. Bohr's model provided a bridge. When an electron jumped from a higher energy level to a lower one, it released a photon with energy equal to the difference between the two states. This direct relationship between electron transitions and light emission connected the microscopic world to observable phenomena. It explained why hydrogen produced spectral lines and why elements displayed unique emission patterns. Energy was no longer an abstract, continuous flow. It existed in packets quantized and measurable. The concept of quanta, first proposed by Planck for radiation, now had a clear application within the atom itself. Quantum jumps made the invisible processes of energy transfer visible and understandable, transforming abstract theory into concrete prediction. The philosophical consequences of Bohr's quantum jumps were equally profound. Scientists had long assumed that the universe operated deterministically, that is, given initial conditions, the future could be predicted with absolute certainty. Bohr shattered this assumption at the atomic scale. While the energy levels themselves were precisely defined, the timing of an electron's jump could not be predicted exactly, only the probability could be calculated. The microscopic world was inherently probabilistic, governed by statistical laws rather than strict causality. This realization forced a fundamental reassessment of how reality could be understood. Certainty was replaced by likelihood, and observation became an active participant in determining outcomes. Bohr's quantum jumps were not just a physical phenomenon, they were a philosophical challenge to human assumptions about predictability, continuity, and the nature of reality. As experimental tools evolved, scientists were able to observe the effects of quantum jumps with ever-increasing clarity. Techniques such as single-ion trapping, laser cooling, and precise spectroscopy allowed researchers to detect individual electron transitions in real time. The once theoretical leaps proposed by Bohr became observable events, measurable with extraordinary precision. Electrons were seen to jump, photons were released, and the quantized behavior of matter was confirmed beyond any doubt. The gap between theory and experiment narrowed, reinforcing the power of Bohr's vision. What had started as a mental model to explain spectral lines became a verified reality, cementing Bohr's place as a pioneer of quantum physics. The practical applications of quantum jumps are extensive and transformative. Lasers, for instance, operate directly on the principle of electrons moving between energy levels. The coherent emission of light that powers laser cutting, medical devices, telecommunications, and countless modern technologies is a direct consequence of controlled quantum transitions. Semiconductors, which form the backbone of all electronic devices, rely on the manipulation of electron states to regulate current and information flow. Quantum jumps are at the core of these processes, illustrating how abstract theoretical concepts can have profound and tangible impacts on the world. The technologies that define modern life, computers, smartphones, GPS systems, and medical imaging, owe their existence to the behavior of electrons following the rules Bohr first described. The discovery of quantum jumps also provided a new lens through which to view chemical reactions. The energy required to move electrons from one level to another dictated the way atoms combined and interacted. The colors of chemical emissions, the absorption of light, and the formation of bonds could all be traced to the quantized behavior of electrons. Bohr's model connected atomic physics directly to chemistry, offering a unified understanding of matter that spanned multiple scientific disciplines. From the simplest hydrogen atom to complex molecular structures, quantum jumps dictated behavior at the fundamental level. This understanding allowed chemists and physicists to predict reactions, design experiments, and explore new forms of matter with unprecedented precision. Bohr's insight into quantum jumps reshaped education and research as well. Students of physics encountered a universe where the rules were no longer intuitive, where electrons defied smooth motion, and where probability replaced certainty. Textbooks began to teach energy levels, quantum transitions, and photon emission as fundamental principles. Laboratories adopted new methods to measure and manipulate electrons, leading to generations of researchers trained to think in terms of discrete states and probabilistic events. The intellectual culture of physics shifted, embracing complexity and counterintuitive concepts, and in doing so, laid the groundwork for the rapid advancements that would follow throughout the 20th and 21st centuries. The broader impact of quantum jumps extended even into philosophy and the arts. The realization that the universe operates in discrete leaps, that continuity is an illusion at fundamental scales, inspired thinkers to reconsider the nature of time, change, and reality. Quantum mechanics, grounded in Bohr's original insights, became a symbol of human ingenuity and the capacity to perceive the unseen. The notion that something could exist in one state and then instantaneously in another captured imaginations, influencing literature, visual arts, and even popular culture. Bohr's quantum jumps became not only a scientific principle, but a metaphor for sudden insight, transformation, and the hidden order of the universe. Even today, the principle of quantum jumps continues to guide cutting-edge research. In the study of quantum computing, scientists exploit the discrete energy states of electrons to encode and process information. In quantum communication, controlled transitions allow for secure transmission of data at the level of single particles. Fundamental physics experiments probe electron jumps to test the limits of quantum theory, explore entanglement, and seek new particles and interactions. Bohr's initial insight, conceived over a century ago, remains at the heart of the most advanced scientific investigations, illustrating the enduring power of a single revolutionary idea. Bohr's idea also exemplifies the interplay between theory and experiment in the scientific method. It shows how a bold theoretical proposal, motivated by inconsistencies in observation, can guide experimentation, leading to confirmation, refinement, and practical application. Quantum jumps were first hypothesized to explain spectral lines, then confirmed through careful measurement, and finally applied in technologies that touch every aspect of modern life. This trajectory highlights the dynamic, iterative nature of scientific progress, where imagination, evidence, and utility intertwine to produce enduring knowledge. In the end, the story of quantum jumps is a story of human curiosity meeting the mysteries of nature. It is a tale of daring insight, rigorous testing, and transformative impact. Bohr's proposal reshaped the understanding of the atom, revealed the discrete structure of energy, challenged classical assumptions, and paved the way for the entire field of quantum mechanics. It connected the invisible behavior of electrons to the observable world, providing a bridge between theory and reality that has guided science ever since. His insight reminds us that the universe often defies intuition, and that progress comes to those willing to embrace the strange, the counterintuitive, and the profoundly beautiful rules that govern existence. Quantum jumps, once a daring theoretical idea, are now a fundamental concept shaping how we understand matter, light, and energy. They illustrate the subtle, intricate, and often surprising mechanisms underlying the world around us. They remain a testament to Bohr's genius, a milestone in the history of science, and a symbol of the transformative power of ideas. Through his vision, we see the universe not as a smooth continuum, but as a structured, dynamic realm of discrete transitions where electrons leap, light is emitted, and the hidden architecture of reality is revealed in all its elegance. At the dawn of the 20th century, the scientific community faced a profound dilemma. Classical physics, which had brilliantly explained the motion of planets, the behavior of fluids, and the principles of mechanics for centuries, suddenly found itself powerless when applied to the atom. Electrons, if imagined as tiny planets orbiting a central nucleus, should radiate energy continuously. According to Maxwell's electromagnetic theory, any charged particle in motion emits radiation, losing energy steadily. The consequence was inevitable: electrons would spiral into the nucleus in an instant, causing the atom to collapse. Yet the world did not implode. Matter remained stable. Atoms, the building blocks of everything, persisted without decay. This contradiction presented a paradox that challenged the very foundation of physics. Scientists were at a crossroads, facing a problem that could not be solved with the familiar laws of Newton and Maxwell. The stability of atoms had become one of the most urgent mysteries of the era. It was into this landscape of confusion and uncertainty that Niels Bohr brought his revolutionary insight. He understood that classical mechanics alone could not explain the resilience of matter. Electrons, he proposed, did not behave like macroscopic objects. Their motion was not continuous, nor could it be described solely by the forces that govern the solar system. Bohr introduced the radical idea that electrons occupy specific, quantized energy levels around the nucleus, each orbit representing a stable state where the electron could exist indefinitely without radiating energy. By confining electrons to these fixed orbits, Bohr effectively solved the problem that had plagued classical atomic models: the instability of matter. No longer would electrons spiral into the nucleus. The atom achieved a form of inherent stability dictated by quantum principles rather than classical forces. This solution was revolutionary because it challenged centuries of intuition. Physicists were accustomed to thinking in terms of continuous motion, where cause and effect flowed without interruption. Bohr, however, demonstrated that the atomic world did not follow this logic. The electron's energy was not a continuum, it was discrete, and it could only occupy particular levels. The notion that an electron could remain stable within an orbit without radiating energy was counterintuitive. Yet it explained phenomena that had previously defied understanding. The classical collapse problem, which had cast doubt on the viability of atomic theory, was resolved in a single stroke. The atom, once unstable in theoretical calculations, now appeared as a harmonious system, stable and enduring, its structure dictated by quantized laws. Bohr's insight did not arise in isolation. It built upon the pioneering work of Ernest Rutherford, who had uncovered the nucleus at the center of the atom. Rutherford's model, while a breakthrough, left critical questions unanswered. If electrons orbited the dense, positively charged nucleus, why did the atom not collapse under the pull of electrostatic attraction? Rutherford's model could describe the structure in a broad sense, but failed to account for stability or the observed spectral lines of hydrogen. Bohr's genius lay in taking the skeleton of Rutherford's nucleus and adding the missing component, a rule for electron behavior. By applying quantization to orbital motion, Bohr provided the solution that classical physics could not: a stable architecture for the atom, capable of explaining both its structure and its observed emissions. The quantized orbits introduced by Bohr also offered an explanation for one of the most puzzling observations of the time: the discrete spectral lines of hydrogen. Classical theory predicted a continuous spectrum, yet experiments showed bright lines at precise frequencies. By confining electrons to fixed energy levels, Bohr demonstrated that these lines corresponded to electrons jumping from one level to another, emitting or absorbing specific amounts of energy in the process. The stability problem was not merely about preventing collapse. It was intimately tied to the behavior of light. The atom's endurance and the structure of its emissions were two sides of the same quantum coin. Bohr's model unified these phenomena, providing a coherent framework that classical models had failed to deliver. The stability achieved through Bohr's quantized orbits had far-reaching implications. It implied that atoms were not chaotic, unpredictable systems, but orderly structures governed by universal rules. Electrons, while invisible and counterintuitive, followed paths that maintained the integrity of the atom. This order allowed chemists and physicists to predict the behavior of elements, laying the groundwork for the periodic table as we know it today. The stability problem, once a source of theoretical despair, became a platform for scientific exploration. By solving it, Bohr opened the door to understanding chemical bonding, molecular formation, and the interactions that constitute matter itself. The elegance of Bohr's solution also lay in its simplicity. The principle was clear: electrons occupy only certain energy levels. These levels are stable. Transitions between them involve discrete amounts of energy. Within these rules, the atom functions as a durable system. This approach contrasted sharply with the endless complexity of classical calculations, which could not account for the electron's apparent suspension in orbit. Bohr's model was both mathematically tractable and conceptually satisfying. It provided an intuitive visualization, a set of stable orbits akin to planetary rings, though governed by entirely different principles. The atom could now be studied, predicted, and understood with confidence, something classical models could never achieve. Bohr's solution to atomic stability also heralded a shift in scientific methodology. It demonstrated that assumptions derived from macroscopic experience could not be blindly applied to the microscopic world. The failure of classical physics at the atomic level highlighted the need for new principles, new forms of reasoning, and ultimately, a new framework: quantum theory. Bohr's quantized orbits were the first step in this direction, showing that stability could be achieved not by refining old models, but by embracing entirely new concepts. The resolution of the stability problem was, therefore, not merely a technical achievement. It was a philosophical breakthrough, redefining the scope and limits of scientific explanation. The model also provided a powerful predictive tool. By knowing the allowed energy levels, scientists could calculate the energy emitted or absorbed during transitions, explaining spectral lines with remarkable accuracy. The classical instability problem was no longer a barrier to understanding, it became a key to unlocking deeper knowledge about the atom. Bohr's quantized model allowed physicists to move from observation to prediction, turning previously mysterious phenomena into explainable patterns. This predictive power cemented the model's importance, demonstrating that solving the stability problem was not just a theoretical exercise, but a practical breakthrough in understanding nature. Beyond the theoretical implications, the stability problem had real-world consequences. Understanding why atoms do not collapse is fundamental to all matter, from the air we breathe to the stars in the sky. If classical predictions had held, matter would be inherently unstable, and the universe as we know it would be impossible. Bohr's resolution provided a foundation for the structure of matter, explaining why atoms persist, why molecules form, and why chemical reactions are consistent and reliable. The stability of the atom is not a trivial matter. It is the underpinning of existence itself. By addressing this problem, Bohr connected the abstract world of physics to the tangible reality experienced in everyday life. Bohr's approach also encouraged a new generation of physicists to explore the boundaries of knowledge. His solution demonstrated that the microscopic world could be understood through a combination of theoretical innovation and experimental validation. By introducing quantized orbits, Bohr provided a framework that could be refined, tested, and extended. It inspired future breakthroughs, from Heisenberg's uncertainty principle to Schrödinger's wave mechanics. all building upon the foundation of atomic stability established by Bohr. The resolution of this problem was therefore both an endpoint and a beginning. It closed a chapter of uncertainty while opening new avenues for exploration. Furthermore, the resolution of the stability problem highlighted the interplay between simplicity and complexity in nature. While the rules governing electron behavior are simple in principle, they give rise to a rich and complex structure of matter, stable atoms, chemical interactions, and the formation of materials all emerge from the discrete energy levels that Bohr proposed. The stability problem was not merely about preventing collapse, it was about revealing the hidden architecture of the universe. Bohr's model allowed scientists to see that order emerges naturally from quantum rules, and that complexity in the macroscopic world is rooted in the structured simplicity of the microscopic. Finally, Bohr's solution serves as a testament to the creative power of scientific thinking. Faced with a paradox that classical physics could not resolve, he imagined a world in which electrons were constrained by quantized orbits, finding stability not in continuous motion, but in discrete, ordered states. This imaginative leap transformed physics, chemistry, and our understanding of matter. The stability problem, once an obstacle, became a gateway to a new era of scientific insight. Bohr's resolution was elegant, profound, and enduring, demonstrating that even the most perplexing problems can yield to bold, innovative thinking. As the implications of Bohr's quantized orbits became apparent, the significance of his solution to the stability problem resonated far beyond theoretical physics. The classical atom, which had once threatened to collapse under its own laws, was transformed into a durable, predictable system. Electrons, confined to discrete energy levels, maintained their orbits without radiating energy, a feat that classical physics could never achieve. The atom, once considered unstable and mysterious, now appeared as a harmonious, self-consistent structure. This insight not only resolved a long-standing paradox, but also established a framework that would support the rapid development of quantum theory. Bohr's solution to the stability problem became a cornerstone of modern physics, demonstrating the power of innovation to bridge the gap between observation and understanding. The elegance of Bohr's approach lay in its ability to unify seemingly disconnected phenomena. Prior to his work, the emission spectra of elements were poorly understood, and the stability of matter remained an unresolved crisis. Classical mechanics could predict neither the persistence of electrons in orbit nor the discrete wavelengths of light emitted by atoms. By introducing quantized orbits, Bohr provided a single principle that explained both. The electron's confinement to specific energy levels accounted for atomic stability, while transitions between these levels produced the observed spectral lines. This dual explanatory power elevated his model from a mathematical curiosity to a fundamental law of nature. It was a rare instance in the history of science when a single idea could simultaneously resolve a theoretical dilemma and predict observable phenomena with remarkable precision. Bohr's resolution of the stability problem also reshaped the philosophical understanding of the atom. Before Bohr, atoms were imagined as miniature solar systems, their behavior assumed to mirror the macroscopic world. The laws of motion and electromagnetism, proven on large scales, were expected to govern the microscopic realm as well. Bohr's quantization shattered this assumption. The microscopic world operated under its own set of principles, distinct from those of classical physics. Electrons did not radiate energy in a continuous manner. Instead, their motion was governed by discrete rules, appearing stable where classical theory predicted collapse. This realization forced physicists to accept that intuition derived from everyday experience was not always reliable. Nature, particularly at the atomic level, could behave in ways that defied common sense, yet remained consistent and measurable. The predictive power of Bohr's model further reinforced its significance. By knowing the allowed energy levels, scientists could calculate the energy changes that occurred during electron transitions, directly correlating with the emission or absorption of light. This provided an exact framework for understanding the hydrogen spectrum, which had long puzzled researchers. The stability of the atom and the patterns of spectral lines were two aspects of the same phenomenon. Bohr's model not only prevented the theoretical collapse of electrons into the nucleus, but also explained the behavior of light emitted by atoms. Classical physics had failed on both counts. Bohr's solution achieved both simultaneously. In doing so, he demonstrated that the stability problem was not an isolated theoretical issue, but a key to unlocking the deeper structure of matter. Bohr's work also illuminated the underlying simplicity within atomic complexity. Although the behavior of electrons might appear chaotic from a classical perspective, their confinement to discrete energy levels imposed order. The atom became a system where energy and structure were quantized, predictable, and reproducible. This order provided the basis for the chemical behavior of elements, the formation of molecules, and the periodicity observed in the periodic table. The stability problem, once a source of confusion, was now a window into the principles governing the natural world. Bohr showed that stability arises not from the continuous laws of classical physics, but from the discrete, quantized rules that define electron behavior. The success of Bohr's model encouraged further exploration into the limits of classical physics. His resolution of atomic instability highlighted the need for new conceptual frameworks to describe microscopic phenomena. It became clear that macroscopic laws, while successful in everyday applications, could not explain the behavior of the atomic world. Bohr's quantized orbits provided the first practical framework for understanding atoms, paving the way for the development of quantum mechanics. The stability problem, once a barrier to scientific understanding, became a catalyst for the emergence of an entirely new field of physics, transforming the intellectual landscape of the 20th century. Bohr's solution also offered insights into the conservation of energy at the atomic level. By confining electrons to stable orbits, energy could be emitted or absorbed only during discrete transitions between levels. This principle reconciled the apparent paradox of radiation without collapse. Electrons did not gradually lose energy as classical theory predicted. Instead, they remained stable until a transition occurred. Energy was conserved in discrete quanta, and the atom remained structurally sound. This understanding provided a critical bridge between classical concepts of energy and the emerging principles of quantum theory, demonstrating that stability and quantization were inseparable. The practical consequences of Bohr's solution to the stability problem are profound. Modern chemistry, materials science, and atomic physics all rely on the principle that electrons occupy stable energy states. The structure of molecules, the formation of chemical bonds, and the behavior of matter under various conditions can all be traced to the stability of atoms. Without Bohr's insight, the predictive power of chemistry, and the development of technology that relies on atomic behavior would have been severely limited. From electronics to spectroscopy, lasers to semiconductors, the durability and functionality of matter rest upon the stability that Bohr's quantized orbits provide. Bohr's resolution of atomic stability also influenced the methodology of scientific inquiry. It demonstrated the necessity of combining bold theoretical innovation with empirical evidence. Classical calculations had failed because they did not account for quantization. Bohr's insight was theoretical, yet it aligned perfectly with observational data, particularly the hydrogen spectrum. This integration of theory and experiment became a hallmark of quantum physics, guiding subsequent generations of researchers. By addressing the stability problem through quantization, Bohr exemplified how creative thinking, grounded in observation, can resolve long-standing scientific paradoxes and open new frontiers of knowledge. Furthermore, Bohr's solution to atomic stability highlighted the interplay between simplicity and complexity in nature. The rules governing electron behavior are simple in principle. Electrons occupy fixed energy levels. Yet these simple rules give rise to the intricate patterns of atomic spectra, chemical reactivity, and material properties. The stability problem, once a source of confusion, revealed the elegant architecture underlying the natural world. Bohr's model demonstrated that stability does not emerge from continuous motion but from the orderly quantization of energy, a principle that underpins both atomic structure and the vast complexity of matter. The philosophical impact of Bohr's work cannot be overstated. By solving the stability problem, he forced physicists to rethink the universality of classical laws. The atom, once assumed to mirror the macroscopic world, revealed a hidden order that required a fundamentally new perspective. Electrons, stable in quantized orbits, exemplified a reality where traditional intuition fails, yet empirical evidence prevails. Bohr's model became not only a scientific achievement, but a philosophical lesson, illustrating that understanding the universe may require abandoning familiar assumptions and embracing new, sometimes counterintuitive principles. Bohr's model also served as a foundation for future discoveries in physics. The stability of electrons in quantized orbits provided the platform on which Heisenberg, Schrödinger, Pauli, and Dirac could develop the full machinery of quantum mechanics. The resolution of atomic instability was the starting point for more advanced theories describing electron behavior, particle interactions, and quantum phenomena. Without the clarity provided by Bohr's solution, the subsequent construction of quantum mechanics would have lacked its critical empirical and conceptual basis. The stability problem, once a theoretical stumbling block, became the cornerstone of an entirely new understanding of the universe. Even in contemporary physics, the consequences of Bohr's resolution of atomic stability remain evident. Quantum chemistry, nanotechnology, and modern materials science all rely on the principle that electrons occupy stable energy states. Atomic clocks, lasers, semiconductors, and countless other technologies function because of the predictable stability of electron orbits. The theoretical insight Bohr provided more than a century ago continues to shape both fundamental research and practical applications. The problem of instability, once seemingly insurmountable, has become a foundation for the most precise and transformative technologies humanity has developed. Finally, Bohr's solution serves as a testament to the power of bold scientific thinking. Faced with a paradox that threatened to undermine classical physics, he proposed a radical, counterintuitive model that not only resolved the stability problem, but also predicted observable phenomena with remarkable accuracy. His quantized orbits provided order where chaos had seemed inevitable, and they revealed the hidden architecture of the atom. The solution to the classical instability problem was not just a technical achievement, it was a profound reimagining of the microscopic world. Bohr's insight transformed atomic physics, enabled the development of quantum mechanics, and established principles that continue to guide our understanding of matter and energy. The behavior of light had long puzzled scientists. While the wave theory of light explained interference and diffraction, it could not account for the discrete spectral lines emitted by elements. Observations of hydrogen, in particular, revealed bright lines at precise wavelengths, like signatures of the atom itself, yet classical physics offered no explanation. It was into this enigmatic territory that Bohr's model stepped, providing a framework that connected the microscopic motion of electrons to the macroscopic phenomena of light. He proposed that electrons existed in specific energy levels around the nucleus, and that transitions between these levels were responsible for the emission or absorption of light. When an electron jumped from a higher energy state to a lower one, it released a photon whose energy corresponded exactly to the difference between the two states. Conversely, when an electron absorbed a photon of the right energy, it could leap to a higher orbit. In this way, the atom itself became a kind of energy exchange machine, regulating light in discrete, predictable packets. The genius of this insight lay in its ability to unify seemingly disconnected observations. The spectral lines, once mysterious, now had a clear explanation rooted in the fundamental structure of the atom. The hydrogen spectrum, for example, followed a precise pattern that could be calculated directly from the allowed energy levels. Each line in the spectrum corresponded to a specific electron transition, a leap between quantized states. This not only explained why certain colors appeared in the emission spectrum, but also why no intermediate frequencies existed. The atom did not radiate energy continuously, it emitted or absorbed light only in discrete quanta. Bohr's model transformed the abstract idea of energy levels into a concrete explanation for one of the most puzzling experimental observations in physics. Moreover, Bohr's approach revealed the profound connection between matter and radiation. Light was no longer an independent phenomenon moving through space. It was intimately tied to the structure of the atom. Every photon emitted or absorbed was a direct consequence of an electron's motion between energy levels. The rules governing these transitions imposed order on what had once seemed random or chaotic. The discrete nature of the emitted or absorbed light reflected the underlying quantization of the atom. In essence, the spectral lines were a visible manifestation of the invisible architecture within. A signature of the electron's allowed orbits and the energy they contained. This understanding also laid the foundation for future developments in quantum physics and technology. Lasers, spectroscopy, and countless optical devices rely directly on the principle that light interacts with electrons in discrete energy steps. Bohr's insight explained why atoms absorb and emit light at specific frequencies, and how these interactions could be measured, predicted, and harnessed. It connected the microscopic behavior of electrons to the macroscopic phenomena of light, establishing a framework that bridged theory and observation. In doing so, Bohr's model not only illuminated the atom itself, but also illuminated the path for decades of scientific discovery and technological innovation. Bohr's model did more than explain the behavior of electrons within the atom. It established principles that would become the foundation of modern quantum mechanics. By introducing the idea of quantized energy levels, he revealed a universe in which matter operated under discrete rules, challenging centuries of classical assumptions. The atom was no longer a continuous system governed solely by Newtonian mechanics. It was a structured framework where electrons occupied specific states and transitioned between them in well-defined steps. This insight provided the conceptual scaffolding for future physicists to develop a comprehensive understanding of atomic and subatomic behavior, bridging gaps that classical theories had failed to address. The quantization of electron orbits introduced by Bohr showed that energy at the microscopic scale is not continuous but exists in discrete units. This principle became a cornerstone of quantum theory, influencing the work of Werner Heisenberg, who formulated matrix mechanics, and Erwin Schrödinger, who developed wave mechanics. Bohr's concept of quantized transitions between energy levels offered a concrete example of how microscopic systems defy classical expectations, providing both a practical and theoretical reference point. It demonstrated that the behavior of electrons could be predicted with precision using new rules, even if those rules were fundamentally different from those governing macroscopic objects. In essence, Bohr laid the groundwork for a probabilistic, quantized understanding of nature, where certainty is replaced by structured likelihoods and discrete interactions. Bohr's model also introduced the principle of correspondence, which states that quantum results must converge with classical predictions in the limit of large quantum numbers. This insight bridged the gap between the classical and quantum worlds, ensuring that new theories remained consistent with observed macroscopic behavior while explaining atomic phenomena that classical physics could not. It was a conceptual breakthrough that gave quantum mechanics both predictive power and philosophical coherence. By showing how classical laws emerge from quantum rules under certain conditions, Bohr provided a framework that allowed physicists to navigate between the familiar world of Newtonian physics and the strange, counterintuitive realm of the atom. Furthermore, the implications of Bohr's model extended beyond theoretical physics. His quantized energy levels explained spectral lines, chemical bonding, and atomic interactions, forming the basis for quantum chemistry. Understanding how electrons occupy stable orbits and transition between energy states allowed scientists to predict the behavior of elements, design new molecules, and manipulate matter at a fundamental level. These principles underpin modern technologies ranging from semiconductors and lasers to atomic clocks and quantum computers. Bohr's insight demonstrated that the rules governing the microscopic world could have profound, tangible effects on the macroscopic world, connecting theory with experimentation and innovation. Bohr's model also shaped the scientific approach to atomic research. By combining bold theoretical reasoning with empirical validation, he demonstrated that new paradigms could replace outdated models when classical intuition failed. The success of his quantized orbits encouraged a generation of physicists to embrace counterintuitive ideas, to trust mathematical formalism and experimental evidence over visual analogies, and to explore the microscopic universe on its own terms. This philosophical and methodological shift enabled the rapid development of quantum mechanics, creating a foundation that remains central to modern physics. Ultimately, Bohr's work revealed that the atom is a highly organized system governed by quantized laws, laying the intellectual framework for all subsequent advancements in quantum theory. His ideas transformed physics, chemistry, and technology, providing the tools to understand the invisible architecture of matter and energy. Without Bohr's pioneering insights, the development of modern quantum mechanics and the technologies derived from it would have been delayed or impossible. His model represents the bridge between classical understanding and the new, quantum world, a world of discrete states, probabilistic behavior, and boundless scientific potential. The influence of Bohr's work extended far beyond the confines of his laboratory, reaching into the minds of generations of physicists who followed in his footsteps. By challenging classical assumptions and introducing the revolutionary concept of quantized energy levels, Bohr opened a new landscape for scientific exploration. His ideas demonstrated that the microscopic world obeyed rules that were distinct from those of the macroscopic universe, yet they could be described mathematically and confirmed experimentally. This revelation inspired a profound shift in the way scientists approached atomic and subatomic research, encouraging bold theoretical innovation combined with rigorous empirical validation. Young physicists of the early 20th century were captivated by Bohr's model. It provided both answers and questions, explaining atomic stability and spectral lines, while pointing toward deeper mysteries that classical physics could not address. Students and researchers alike saw in Bohr's work a new methodology for understanding nature, one that embraced counterintuitive ideas, probabilistic behavior, and quantization. This approach laid the foundation for the next great leaps in physics, from Heisenberg's matrix mechanics to Schrödinger's wave mechanics, and later to the development of quantum field theory. Bohr's insights created a fertile intellectual environment where curiosity, imagination, and careful calculation could thrive in tandem. Bohr's influence was also personal and direct. Many of the era's leading physicists spent time at his institute in Copenhagen, engaging in discussions that were at once philosophical and mathematical. The Copenhagen Institute became a hub of innovation, a place where young scientists could wrestle with the paradoxes of the quantum world under Bohr's guidance. These interactions shaped the thinking of luminaries such as Heisenberg, Pauli, and Dirac, who went on to expand the frontiers of quantum mechanics. Bohr's mentorship, his insistence on connecting theory with experiment, and his willingness to embrace unconventional ideas inspired a culture of scientific inquiry that emphasized collaboration, debate, and the pursuit of fundamental understanding. Beyond direct mentorship, Bohr's work influenced the conceptual development of physics. His ideas encouraged physicists to think in terms of probabilities, wave functions, and energy quantization, laying the groundwork for modern quantum theory. By introducing concepts such as the correspondence principle, Bohr provided a bridge between classical physics and quantum mechanics, demonstrating how new principles could coexist with established laws under specific conditions. This philosophical insight helped guide generations of scientists in developing theories that were mathematically rigorous, empirically verified, and yet radically different from classical intuition. Bohr's model also inspired technological and experimental advancements. The understanding of electron transitions, energy quantization, and atomic stability motivated precise experiments in spectroscopy, the development of lasers, and the manipulation of atoms for research and industrial purposes. Scientists learned not only to observe the quantum world, but also to harness it, transforming Bohr's theoretical insights into practical applications. This dual legacy of conceptual innovation and technological impact reinforced the enduring significance of his work and demonstrated how fundamental discoveries can ripple across multiple domains of science. Ultimately, Bohr's insights created a framework that continues to shape contemporary physics. The principles he introduced underpin quantum optics, quantum computing, and advanced materials science. Every experiment probing the behavior of electrons, photons, or atomic nuclei reflects the intellectual foundation laid by his work. Bohr's vision revealed that scientific progress often depends on challenging assumptions, embracing uncertainty, and daring to imagine the unseen. By doing so, he inspired generations of physicists to explore deeper, think more boldly, and expand the boundaries of human knowledge. His legacy is not merely in the model he created but in the mindset he instilled, a relentless pursuit of understanding the fundamental workings of the universe. The impact of Bohr's work has extended far beyond the early 20th century, shaping both modern science and technology in ways he could scarcely have imagined. His model of the atom, with its quantized energy levels and electron transitions, provided the foundation upon which the entire edifice of quantum physics was built. Today, researchers around the world continue to rely on principles first articulated by Bohr to probe the behavior of matter at its most fundamental level. From the tiniest subatomic particles to the complex machinery of modern electronics, the imprint of Bohr's insights is everywhere, guiding experiments, informing theory, and inspiring innovation. In laboratories across the globe, scientists manipulate atoms and electrons with extraordinary precision, a practice rooted directly in Bohr's discovery that electrons occupy discrete energy levels. Techniques such as laser cooling, ion trapping, and quantum state control allow researchers to observe individual electrons and even control their transitions, confirming the enduring relevance of Bohr's work. Every photon emitted or absorbed in these experiments represents a direct echo of the principles he established. By revealing the structured, predictable nature of the atom, Bohr provided the conceptual tools necessary to explore phenomena that were once considered beyond the reach of human understanding. Bohr's legacy also underpins countless technological innovations. Lasers, which rely on electrons moving between energy levels, have revolutionized communications, medicine, manufacturing, and scientific research. Semiconductors, which form the backbone of all modern electronics, operate on the manipulation of electron states, a principle entirely dependent on the quantized behavior first proposed by Bohr. Atomic clocks, essential for global positioning systems and precise timekeeping, function because of predictable electron transitions in atoms. Even quantum computing, poised to transform computation, depends on the principles of superposition and discrete energy states, ideas that trace their lineage back to Bohr's model. The practical applications of his insights demonstrate how fundamental discoveries in theoretical physics can ripple outward, shaping technology and society in profound ways. Beyond technology, Bohr's influence persists in the way science is conducted and conceptualized. His work established the importance of integrating theory with experiment, of embracing models that may initially defy intuition but accurately describe reality. The Copenhagen interpretation of quantum mechanics, which Bohr championed, emphasizes the role of observation in defining outcomes, a philosophical shift that continues to influence research across physics, chemistry, and beyond. Bohr's approach demonstrated that understanding the universe often requires rethinking assumptions, questioning classical paradigms, and developing new frameworks capable of capturing phenomena invisible to the naked eye. Bohr's legacy also inspires education and the cultivation of future scientists. His model of the atom is taught worldwide, forming the foundation of physics curricula and introducing students to the counterintuitive yet elegant principles of quantum theory. By illustrating how bold theoretical ideas, grounded in evidence, can transform understanding, Bohr provides a model for scientific creativity and rigor. Each new generation of physicists, chemists, and engineers builds upon his insights, expanding the frontiers of knowledge and applying them in ways he could not have predicted, from nanotechnology to quantum information science. Ultimately, Bohr's contributions remind us that scientific progress is cumulative, that the insights of one mind can resonate across decades and disciplines. His vision of the atom as a structured, quantized system transformed not only physics, but the very way humanity understands the natural world. From fundamental research to everyday technology, from education to philosophical reflection, Bohr's legacy endures, a testament to the power of curiosity, imagination, and rigorous inquiry. The atom he revealed continues to guide exploration, inspire discovery, and shape the modern world, proving that the influence of a single scientific breakthrough can echo far beyond its origin, touching every facet of human knowledge and endeavor.